Welcome back for our second session on the next generation Eurocodes. Metal and glass are emblematic features of modern architecture. We, however, will be having a structural look at them, starting with the backbone of most industrial structures, steel. This talk will be given by the outgoing chair of SC3, Ulrike Kuhlmann. Thank you, Ms. Kuhlmann.
So thank you very much for the nice introduction. It's a pleasure for me to be here and explain a little bit on the development of Eurocode 3 design of steel structures. And this presentation has not been done by my own and my co-workers, but it was a common work also by with Markus Knobloch, Professor Markus Knobloch and his team. Professor Markus Knobloch is my successor since October last year on the chair of SC3, and we both agreed that I'm giving the common talk, but he will be available for the questions afterwards. So let's continue. This screen gives a kind of summary of the structure and overview of the existing Eurocode 3. So in fact, there are 20 parts, 12 are general parts, and 8 are application parts. Among the general parts, there is, for example, Part 1.1, General Rules and Rules for Buildings, mainly on member stability, and a design of joints, which I think are the two main important parts which everybody needs. But of course, among the general parts are also some very specific items. For example, Part 1.4, stainless steel, or Part 1.11, tension components, which probably only a small group of users will use. Then coming to the application part, for example, Part 2 for bridges. The application part form a kind of master to give reference to the general part, for example, bridges to Part 1.5 or Part 1.9, plated structures and fatigue, and of course also to the other Eurocodes, for example, the Eurocodes of loading, which we just heard about. So this is a link, this is an important link to give these references. Coming to the strategy, and I'm not repeating what Steve has already presented as a strategy for the second generation of Eurocodes. I just give the main key points here. Already in 2013, as SC3, we decided to establish some principle for the further development of Eurocode 3. They are fully in line with the general principles of TC200, but of course some are a bit specific. So for example, we decided to keep the overall structure of the Eurocode 3 and its parts. We decided to improve the clarity, harmonize and simplify rules. That is very similar to the general guidance, but also we wanted to have a focus on the harmonization between the different parts of Eurocode. We want to reduce the overall volume, for example, by avoiding these many existing informative annexes, and reduce the number of alternatives, which, for example, was especially important for Part 1.1, where we had a number of alternatives for lateral torsional buckling. So I think these are some main aims. The procedure, it was explained by Steve Denton just, was within the mandate F15. We as SC3 had 13 project teams or tasks, and they were organized in these 4 phases, so 4 overlapping phases. And the organization was on purpose. So we had Part 1.1, Part 1.8, the basic parts in the first phase. And then a phase 2 mainly on stability, a phase 3 mainly on materials, and at the very end, the application parts. So for example, the project team of the application part knew already what was in part 1.9 or what was in part 1.5, and we avoid repetition. We allow for references. So I think this was a good scheme to have that. I'd like to give you a few ideas on what I understand under structural reorganization. So we have at the moment a part 112 dealing with additional rules for the extension of Eurocode 3 up to steel grades S700. This content is now shifted to the original parts, so part 1.1, part 1.5, part 1.8. So I think this is very a good metaphor for clarity and enhanced ease of use. However, before we dissolve part 112, we decided to have a new part 112, now covering the very high steel strengths up to S960. In fact, I must admit, it's not yet fully, it's a draft, it's not yet finalized completely. So for example, there is a need for the extension of buckling rules, and there is a need for additional rules for connections. However, I think this idea is fully in line with the mandate that we want to introduce or increase or open the gate for new findings, such for example, new materials. We are working in altogether now 22 working groups, and each of the working group is organized with one part, is responsible for one part. So we have 14 responsible for the general parts and 7 working groups responsible for the application part. And you can see here the working group numbers and also the current conveners of that. These working groups are groups of experts, experts for that special subject, and they are nominated by the national standardization bodies. So we achieve two issues. We have a real European group of experts for this sometimes very specialized subject. And on the other hand, we have they are sent by the national standardization bodies. So in fact, they represent somehow the view of their country. So I think it is an important part of this consensus building we also heard about, to have these technical conditions clarified within the working group. I'm now coming to main changes, but mainly in view of innovations. And I follow the different phases, but I'm not complete. So I pick some of the parts and some of the cases. Let's start with part 1.1. Part 1.1 for me is the success story we have. So we went through the whole procedure now, and we got the formal vote unanimously, and we have the document published now by CEN in November last year. But it's also a success story in technical issues. So we succeeded to summarize, to simplify, to bring together all the different alternatives for the stability rules. And we also have an extension for S700. So for example, das war zu viel. So. You see here, for the buckling curve, an extra column for steels between S460 and S700. I already started with this. I think this is also an important point of our new part 1.1. We created a special section which gives a link between the method of analysis and the type of verification. Method of analysis in our case means mainly need of second order analysis or not, need of certain imperfection or not. So there are certain criteria which makes this decision, and we identified altogether six methods, and these were organized according to this flow chart, also in the structure of the chapter. So there is M0 at the top, first order analysis without any imperfection, the most simple case. And there is M5, the most complicated case, imperfection in both direction, also second order analysis in both direction, including the torsional effects. So I think by having the complexity organized in such a flowchart, this flowchart is not only of help for us when we were drafting that, but it is also of help for the users. A second part of our phase 1 is part 1.8. Again, this is very important for us. Again, we had a restructuring for ease of use. But we also have here, very important, a harmonization with EN 1090 Part 2, which is the code for execution of steel structures. We had some innovations included, like threaded holes, for example, or the Annex C improved normally pin connection, or Annex D design of column bases, which also has a kind of harmonization with Eurocode 2 Part 4. So for me, this is not only enhanced ease of use and clarity, but it's also an improved harmonization with other codes. I want to pick also one issue under this item, and I was personally involved in that. So this is the welding of high-strength steel. We introduced a new resistance formula, as you can see here, for the fillet weld of high-strength steel. And this new resistance formula has not only the strength of the parent material, but also the strength of the filler metal included. And you can see here from the factors, it gives the filler metal 75% of the strength. So this is really dominating the strength of fillet welds. And we can achieve by that a so-called overmatching, so higher steel strength. That means an increase of the strength, but also undermatching, for example, to achieve a certain ductility or better weldability. So this opens the situation for steel grades higher than S460. For butt welded connection, the situation is a bit different. We discovered when welding high strength steel, S700 for example, that there is the danger that next to the weld, we have something which we call soft zone. So this soft zone might lead to a failure in the heat effective zone or in the weld itself. And of course, a reduction of the strength of that. So for this situation, we also developed a new rule, and also a rule which covers the soft zone, but also something which covers the filler metal. Yeah? So I think this is an increase in the view of high-strength steel and make high-strength steel more applicable. Coming to phase 2, fire design. Here the situation is that the positive decision to send to formal vote has been done. So the formal vote will start in October this year. We have a number of changes. One, for example, which is true for all the fire parts. There has been a harmonization across all the fire parts. We have increased rules for high-strength steel, some new rules for hot dip galvanized steel, for stainless steel. So this is an increase, of course, of knowledge. But I again want to pick one item. This is the increased possibility to use advanced design method. So to calculate the structural behavior in case of fire based on a thermal analysis as well as based on a mechanical analysis, and do this calculation not only for just a member, define the member resistance against fire, but have the structural behavior of a whole structure also in view of natural fire scenarios. So this is an increased possibility, I think, very important for the future. Let's come now to phase 2 again, plated structural elements, plate buckling. Here we are also in the same situation that in October this year we will have the formal vote. Myself, I'm working group leader of this group, so I know a bit about the history behind. And we started to develop improved rules and changes or additions already before the mandate started. And these improved rules were so-called new amendments, were collected, I always said, in a basket, so that when the real project team work started, they had already accepted also on the level of SC3 a number of changes they could introduce in the new draft. So that was a very positive decision we could do. And this concerns a lot of items. I give you here some example. For example, we have new rules for corrugated webs. Biaxial compression is dealt. We have these rules for tapered panels here, new ones. We also have a restructuring of the whole draft. So in fact, the original Annex C dealing with finite element method has been moved to Part 114. The original Annex D and Annex E, the content of that, has been integrated into the main text. So at the end, we even could reduce the number of NDPs from 15 to 3. So I think this is really an improved structure. And I also want to give you a direct examples. This example concerns the famous chapter or section 10, reduced stress method. In fact, I must admit that this existing section or this method, reduced stress method, is more or less only used in German-speaking countries. Because we have something like a Leitfaden, a guidance book. So what we did here is to have a complete restructure of this chapter, of this section, following also a flowchart, as you can see here. And I think this is, of course, an enhanced ease of use and should allow also non-German speaking users to apply this method. Coming to phase 3, fatigue is involved in that. That is Part 1.9. Here we are at the moment in the Sen inquiry stage. So the Sen inquiry is running. Also we have ease of use in view of more exact definitions, clear statements, for example, on the required weld quality. And we have, which is important, better harmonization with EN 1090 Part 2 for the execution. In fact, the original Part 1.9 was drafted before 1090 existed. So there were some discrepancies between them. And now we have clearly in Part 1.9 only supplementary rules, requirements to the EN 1090 rules. We also have improved resistances for light notches, and we have extended the scope. For example, there is an Annex B, hotspot stress method, and a new Annex C for effective notch stresses. And this is, of course, again, including new content and trying to open the gate for new application. Improving clarity is very important in this sense, and you can see as an example the new detail tables. This is what everybody needs when he does a fatigue verification, to classify the detail. And these detail tables have been reorganized, the figures have been really improved, and we added also a symbol for the weld. So I think this is, yeah, it's a big advantage now. We also added a new informative annex, fatigue design of welded joints subjected to high-frequency mechanical impact treatment. This HFMI treatment is a post-weld treatment which allowed to increase the fatigue strength really drastically. So it's a new method, but it is especially interesting for high-strength steel, because the use of high-strength steel under fatigue is not of any advantage normally. But having this treatment, you get a real profit from that. And personally, I think that these innovative methods also will be of importance for what we heard already, for the renovation, rehabilitation of existing structure. Coming to the application parts, for example, part 2 bridges. Here there is the positive decision to send the part to SEN inquiry, and the SEN inquiry will start in March next year. We have some small changes concerning better wording or including other methods. We have, as it was already referenced to, we have moved the content of the former Annex A, dealing with bearings, and the former Annex B, dealing with expansion joints. The content has been moved to EN 1090, and in fact, the content as it is, these annexes were not only valid for steel bridges, but for bridges in general. So this is a very consequent restructuring. We have a new Annex A dealing with design of hangers for tight arch bridges, and perhaps this is a bit a special feature, because by fulfilling construction rules, you succeed as user avoidance of vibration of these slim elements, but also you do at the same time fatigue verification. So this is a very useful scheme for that. Coming now to piling, part 5. Here we also have some new rules or enhanced rules for buckling especially. Part 5 followed part 1.1 and applied these new rules or extended these new rules for their Z and U piles especially. They also have a flowchart included now, and we also have a better harmonization with Eurocode 7 included here now. So in fact it is a big improvement, but perhaps more in steps than said. Coming to crane supporting structures. Here the start is in March 2024 of the SEN inquiry. We have ease of use, adding a clear definition of the interface between cranes and the supporting structure. I think this was very important, and it is a big advantage in comparison to what we have at the moment. What we could not achieve, though we tried to have the crane scope extended, it is still lined up only for bridge and gantry cranes, so there is not a big extension. But for those cranes, it's a really big improvement we achieved. Also harmonization, of course, with part 1.3. For example, concerning fatigue, there were the lambda factors, the damage equivalent factors were originally in part 1.3, but they are of course steel specific. So they have been moved now to part 6. I think it is really in all sense an improvement, including also for this issue a flowchart. Let's come to our new part 1.14. Design assisted by finite element analysis. And in fact, this is not completely new. We have had as a core element the Annex C of part 1.5 and also the rules in part 1.6 for shell elements. But we decided to have this now valid for all applications. And giving rules for the use of finite element analysis and other numerical methods in the design of steel structures for ultimate limit state, including fatigue and serviceable limit state. And by doing that, a lot of clarification of the method or clarification also of expressions were done. Giving you an example, there is now a clear differentiation between validation and verification. Validation comparing with the physical, the modeling with a physical existence, for example, by comparing with tested, and verification means more the mathematical correctness. And we also have a direct resistance check included with an extra partial factor, gamma Fe, which only covers the difference between modeling and the physical reality, not any kind of distribution. The gamma M factors are kept for the definition. We will have a background and commentary on that, and I think this is very useful. And I think this new part 114 will be a future-oriented tool to take care of the increasing importance of numerical simulation and design by analysis, ensuring at the same time the same level of safety. So I think this is an important point. I come to the summary and conclusion. So I think we exceed by far achieving these general aims as they are given out. And this achievement could, I think, be achieved by having this clear organization of working groups, responsible always for one part, working groups of experts. We had this staggered development within the 4 phases, which was an advantage, I think. We had a very stringent review process for each of the project team drafts and also of the final document by introducing an extra review of the so-called technical approval. And of course, all that is very much dependent and could only be achieved by a high and strong involvement and support by practitioners and scientists included in the working group, but also in the national by commenting. So we want to thank all our colleagues for their strong support, and especially our secretariat by Susan Kemper. And let us work together and influence the development, create codes for the future. Thank you very much for your attention.
Thank you very much, Ms. Kuhlmann, for this presentation, for sharing success stories of good cooperation and effective technical work with us. For those of you who have joined us recently, there is a question and answer session at the end, so just start sending in your questions. And also, I have one lost and found announcement. A card, probably a key card for a hotel. Come and find me at the lunch break. Okay, we continue with aluminium. Aluminium made its first appearance in structural design in the 1930s. Today, it is widely used in the form of profiles, connectors, and sheeting. Alberto Mandara will give us an update on the state of the art, as described in the upcoming Eurocode 9.
Thank you. Thank you very much. It is a great pleasure for me to stay here in Berlin with your kind invitation to present the development of Eurocode 9 on aluminium structure. I'm going to present this presentation also on behalf of Federico Mazzolani, who was the former chairman of SC9 committee. And he can be considered as the father of both research and codification in the field of aluminium structures for both civil and industrial applications. The history of codification this is the general content of EASY 9, which reflects the content of the presentation. EASY 9, Eurocode 9 is divided into 5 parts, namely part 1.1 dealing with general structural rule, part 1.2 dealing with fire, part 1.3 dealing with fatigue, Part 1.4 dealing with coal-formed structural sheeting, and Part 1.5 dealing with shell structures. The history of Eurocode 9 is a little bit different from the history of other Eurocodes, in the sense that in the ENV version, that is the first version, just the first 3 parts were developed. The second part 1.4 and part 1.5 were developed later, that is during the conversion phase to EN, and this was a request mostly from the aluminium industry, which asked for a specific codification on these topics. It is to be underlined that for these topics, cold-formed and shell structures, Eurocode 9 is the first codification at European level, accepted at a European level. So a little bit of history about the aluminium structures. The beginning is at the beginning of the 70s of last century, almost 50 years ago, about 50 years ago. And a first achievement was the European recommendation for aluminium alloy structures issued by the ECCS. Then in 1992, there was the establishment of the SC9 committee devoted to Eurocode 9. The first edition, the EN version of EASY 9, is in 2007 and revised 2009. And the second generation of aluminium code represents the end point of this half-century-long process. So, what is new in the Eurocode now of second generation with regard to aluminium alloy structures? The new contains the developments of the code was made strictly following the rules of SEN, and most of all, we worked in the spirit of simplifying the code, simplifying the rules, clarifying the several points, harmonize both the code, both in its internal parts and with regard to the other Eurocodes. And in the end, we also reduced the number of the nationally determined parameters, which I've seen is a common task of every Eurocode. Likewise, most additions were made in part 1.1, whereas the other parts were just marginally modified. So, in which way we enhanced the use of Eurocode 9? First of all, optimizing the editorial layout, general improvement of Word in general, improvement of figure. The calculation methods have been simplified as far as possible. There was some specific distinction between buckling of members depending on the type of weldings, and also the effect of initial bow imperfection on buckling. This is for aluminium. This aspect it is important because of extrusion of aluminium, which is susceptible to give an initial bow imperfection higher than commonly accepted, for example, for steel elements. So, coming to part 1.1, this is by far the largest part of Eurocode. It is the largest document among the 5 composing the Eurocode. And it deals with most of commonly treated subject for structural design of aluminium alloy structures. The major changes in this part are concerned with the introduction of a new material, the introduction of additional structural typologies, namely bridging, roofing, composite aluminium, concrete, and so on. We also introduced, and this is an important aspect of the latest development, a new buckling class. It is important to underline that aluminium alloys are a very, very wide family of materials. That's the why, and the behavior of these alloys strictly depends on both hardening and heat treatment sensitivity of the alloys. The consequence is a behavior which can be very different, in particular when moving from the elastic range to the plastic range. As a consequence of this, also buckling resistance is deeply affected by this behavior, and this led to the introduction of new material classes intermediate between the classes previously defined. Accordingly, we defined also new buckling curves. We also considered the new connection types, namely friction stir welding, ball channels, screw grooves, and so on, in order to strictly follow the peculiarities of aluminium from the technological point of view. Aluminium is a very expensive material, and it can be competitive with other materials, namely steel and stainless steel and so on, only if we optimize some details. And the connection is one of the details which it is more possible to to move in order to find an optimization of cost. There are some additional topics which led in the end to introduce new contents in part 1.1. They are new buckling curves. We are these new special types of connections, as told before. And this resulted also in the addition of new annexes dealing with bridges, lattice space roof structures, composite aluminium concrete beams, modified buckling conditions, and other minor topics. So here are some pictures showing the modification introduced in the code concerning the new buckling curves. Aluminium compared to steel are very sensitive to plastic effects, and this results in the curves being strongly affected in this region around the value of 1 of the normalized slenderness. And this is the distinction between the 3 classes, also considering the presence of a weld, because a weld has been found to be strongly affecting the buckling resistance. New connection types. These connection types take advantage from the extrusion, which is one of the possible ways to produce aluminium members. Extrusion is typical of aluminium members. Steel cannot be extruded. Just a few types of stainless steels can be extruded. But extrusion is a property of alloyed materials, relatively soft materials, such as aluminium and other type of alloys. Because of extrusion, it is possible to get a very good optimization of the profile, which can be tailored to any possible kind of use. And this can represent a way to make a more rational design, so saving money, saving reaction time, and so on. And this is one of the points which can be favorable to aluminium and it can make aluminium competitive as respect to other materials. That's the reason why we consider new connection types. For example, this friction stir weld is an innovative welding process which has been patented at the Welding Institute in Cambridge, UK. And it is possible with aluminium, but not with other materials, and enables the possibility to create very long joints with no filling material and with a very good fatigue response. That's the reason why it was introduced in the code. Other type of connections are mostly based on the extrusion capability of aluminium and are aimed to optimize the connection, in particular in prefabricated elements, let's say. The annex dealing with bridges, of course, has been introduced in order to point out the possibility to have a very special types of deck, also in these cases using extruded profiles, which can be connected, which can be designed, shaped and connected in a proper way, enhancing the capability of extrusion. And this is a typical aspect of aluminium alloys, which has been stressed in the second generation Eurocode. Always on bridges, there are some new details contained in order to point out, emphasize the capability of extrusion. The lattice special roof structures are widely used structural categories in the field of aluminium, because this is the case in which the lightness of aluminium is largely appreciated. And also in this case, codification was somewhat lacking, because there was no specific rules. The design of this element was mostly based on a preliminary test assessment. But now with this part, new information have been added, which enabled the use, the design of this structural category in an easier way. Composite aluminium concrete beams are quite, let's say, an odd topic. It may be quite strange to combine aluminium with concrete for a number of reasons, but there are some applications in which this typology has been appreciated, namely the restoration of existing bridges, old bridges, in which the use of aluminium girders instead of steel girders has been preferred in order to reduce the weight on the existing piers. So there's a number of applications in which this category, structural category, can be useful. And this is the reason it has been included by means of an informative annex, of course, in the Part 1.1 of Eurocode. The other parts have been just marginally modified. The fire, just light modification with respect to the old version, including the reorganization of the text and its coherence with other Eurocodes, improvement of figures and symbols, improvement of clarity and consistency and harmonization of the contents with other parts, in particular thanks to the cooperation with the horizontal group fire, which led to a better harmonization of the contents of the code. The same we can say also for fatigue, which has been not modified so much, apart from the usual improvement in clarity, graphics aspects, and so on. Some details for fillet weld joints have been improved, much like some detail categories for bolted joints. A specific part dealing with the friction stirred welding has been used because stirred welding has been introduced in the first part, so specific details have been added also in the part of dealing with fatigue. Cold format structural sheeting, we have to consider that this part, together with the part 1.5 dealing with shells, have been more recently developed. That's the reason why we can assume that it has already in the, let's say, final stage. So in this part, no particular modification have been made, just a few new contents, such as new general rules for cold format profiles, not only profiled sheeting, new rules for starting overlapping system of sheeting with single or double overlap, new rules for trapezoidal sheeting with side overlaps. And finally, a clarification of behavior of diaphragm at the end of a building. So not very large modifications, but just clarification of already existing part. The same we can say for shell structure. Shell structure has been the latest part to be developed. On this part, also, there was a quite large numerical analysis in order to calibrate the buckling curves for shell structures. It was mostly modeled on the corresponding part 1.6 of EC3, but considering the particular behavior of aluminium alloys, in particular as far as the plastic behavior is concerned, with its consequences on the buckling curves of aluminium. Major changes in this case, in this part, refer to more accurate formulation for imperfection reduction factors given in Annex A. This was a problem arised as a consequence of some feedback from users, according to which it was convenient to revise the formulation of the imperfection coefficients to be introduced in the buckling formulas. As you know, shell structures are very sensitive to both geometrical and mechanical imperfections. And in case of aluminium, these imperfections are strictly interacting with the plastic behavior of typical of the material. That's the reason why special work was done on this aspect, leading to a new formulation of buckling curves and imperfection reduction factor. So the curves were refined on based on the available data. Just minor changes were made in the content list of the document, and a general improved consistency with the corresponding document of EC3, namely part 1.6 of EC3. This was made in collaboration with the ad hoc group of EC3 dealing with the shell structure, the one led by Michael Rotter. So in conclusion, for sure we can see that the Eurocode 9 is an important achievement in the field of codification on aluminium structure. It is the first code accepted at European level dealing with this kind of structures. In December 22 last year, the final draft of second generation EC9 has been unanimously approved for publication by all member countries, and we can say that it encompasses all the whole new policy of CEN TC250 for Eurocode second generation, so we are fully satisfied for this. And in March 23, I was nominated chairman and taking over the historical role played by Federico Mazzolani in this figure. And so we are entering now a new stage of maintenance and feedback from user. Before concluding, I wish to thank Professor Mazzolani, first of all, but also all people who were involved in the development of EC3. In particular, I say thank you to our secretariat, Dr. Roald Segrov, who made and is making still today an unrelenting work in supporting this activity, not only from the technical point of view, but also from the administrative point of view. I also thank the people like Professor Thorsten Oglund and Werner Meder, which were involved in the coordination of project teams, and so on. I, of course, thank you for your kind attention.
And I thank you, Mr. Mandara, for this.
Long.
No, it's perfect. For highlighting to us the peculiarities, but also the advantages of designing with aluminium. Now, structural glass was not included in the first edition of the Eurocodes. A completely new Eurocode is currently under development, and Markus Feldmann has all the details for us.
Yeah, thank you very much for the introduction. And also thank you very much for the invitation for having a speech here at this symposium. Ladies and gentlemen, my presentation is a little bit different compared to the other presentations. So unfortunately, I can't report you on any changes to the old one or for the first generation, because there hasn't been a design code on structural glass on European level. But what I then can report you is how to develop or how to ramp up a Eurocode or a European code for structural design on glass from scratch. And with a smile on my face, I would like to say that this reaches out more than 550 years back. Because the first rules on glass construction are known from the intendant of the Duke of Northumberland in 1567. Because he said that because of the importance of the wind, the glazing of the castle breaks and is lost. Therefore, it would be good that the glass of each frame is taken down and stocked in security when our lordship is out. And then when our lordship comes back, it is not so difficult and quite cheap to put the glass in the frame again, since the reparations due to the glass breakage are too expensive. And this is very, very remarkable, because I believe this lordship is not suspected to be a poor man. And it shows you that it was very valuable and very rare. Today, glass is no more so rare and no more so expensive. It helps us for life, because without light, natural light, there is no life. It helps us for building sustainable structures because of having clever ventilated facades or double-skin facades. Or even for the architecture, it helps that the structure itself gets an artwork. But it's not only these big, impressive things. It's also what we can observe are the structural developments. We are including glass now for columns, frames, beams, staircases, or even for simple fins in a facade, or for beams, or it already has become iconic for some structures, and so on. And that gave rise to develop, or for the question how to make it happen that a design standard for glass will come. And that gives you the current situation. Here we have here Europe, and across all of the countries, there's a variety of existing design standards, all with different approaches, all with different aims, all differently included in legal frameworks. And the question is how to cope with all these mess of different standards, and how to condense a design standard for structural glass that is That is what we are coping with. And that gives me how to develop a route to Eurocode 10, design of glass structures. Well, I don't intend to, again, repeat all the details of how to develop a Eurocode, because earlier this morning, Steve Denton has reported a lot of these roadmaps for the Eurocodes on the whole. I would like only to give you some key dates, because in 2012 we received a specific mandate, M515, in which we then were asked to develop the code in 3 different tasks. The first task was to collect all the information on the current state of the art, how to design glass, and how to incorporate to them to a comprehensive standardization work. That is done with these guidance on European structural design of glass components, which you can see there. And then that gave us then green light for the second task, where we were asked to produce a SEN technical specification, and that has received then the number 19100, design of glass structures. And after having received the formal vote for this, because it's now in power, or it is now on the market, we have been asked to convert this then for a Eurocode in the task 3. And we are just to start the formal inquiry, which all the things will be handed over in September of this year. And then we are hopeful, we hope that then all the things will be going well for a formal vote, and that we then will have a Eurocode 10 on structural design of glass, presumably in 2025, and then will be handed to the nations in 2026. So, and we hope and we think that we are now well integrated in the Eurocode family with the EC10 having this new number. Unfortunately, it was not EN 2000 because this was already given to another code, but we are happy with EN 19100, and then that gives me then the opportunity to give you some words on structure and content of Eurocode 10. The structure and Eurocode of Eurocode 10, and I say Eurocode 10 because today it is CENTS 19100, but all in all it will be Eurocode 10, is consisting of 3 parts plus 1. The first part is on the basis of design and materials, all those bases which are not included in the Eurocode NOT, because glass is a different material, it has a perfect brittleness, and all these needs additional things which we are clarifying in this part. It is then on the safety issues, robustness things, and of course glass strength and further properties relating to the material. The part 2 is then the original design work which we are used to in glass design, and it is mostly related to the lateral loaded components. And this you can see there. In part 3, it is in-plane loaded glass element, and this is a rather innovative part. In part 4 is then additional things which relates to recommendations for the choice of glass, recommendations how to build with glass, and how not to fall through, and how to make barriers, and guidance for specification relating to the risk of human injuries. Nevertheless, this will be remaining in its CENTS status because it interferes too much with national regulation of the different countries across Europe, and that then the decision was that we remain this that this will be remaining in a CENTS. The glass components for buildings has relations to the product standards, CENTS, which is clarified or regulated under CENTS 129. And there we identified that we have already a code which deals with calculation of glass. And then that was an additional task to arrange and to accommodate with those people. And then we succeeded in this, in that way that we say we have harmonized our rules in SC11, in the Eurocode 10, but the rules in the Eurocode are relating to the components on consequence classes 1, 2, 3, And in the product standards, it relates to the components of consequence classes 0. I say 4, because that is too much, but to 0. And what is very important, that there is a clear harmonization, a very smooth transition from the rules of the product standard code and our Eurocode 10 say that, that our rules tie in seamlessly in those of EN 16612. Then let me drop some words on the conceptualization of the Eurocode 10 design rules. Conceptualization in glass design is very important because glass is a perfect brittle material. It does not show any ductility. We must always expect a breakage of a glass ply, always. So also in our design, always. The cause of glass breakage can be anything. So it is a failure of unknown origin. And not only for exceptional load cases, every day. So glass design is literally robustness design. And the Eurocode 10 approach, the answer to this is that a part of all the rules we have given from the working group on robustness, we have incorporated them as well. But we have also some specialities. And this is first the engineering robustness, and secondly the organization of design situation. Let me explain this a little bit more. Engineering robustness, you can imagine, it is if you build up a cross section with different glass plies, and in between you are putting some plastic layers, then you are creating a quasi-ductility, and that creates robustness. And this is a typical issue for cross-sectional engineering robustness, or it can do it structurally in terms of caring for a special detailing. When you have a hole and then you introduce a mortar which is resin-based or anything else. So this is engineering robustness, for which I have given you some examples here in this table. But the second part is very important as well. It is what I call the organizing design situations. Now, let's consider in the traditional materials, we have the ULS and the SLS. So the serviceability limit state and the ultimate limit state, and they are always calculated under the prerequisite that these materials are not fractured, so they are intact. We, in glass design, need to have different additional states, assume where the glass is not yet no more intact. And it is then, of course, consequently, the design for the state during glass fracture. So it is the verification of safe glass fracture, which we are then calling FLS, fracture limit state. And then it is a design for the post-fracture state, say that we have a residual load capacity that we are calling then PFLS in our code, post-fracture limit state. Of course, PFLS and FLS are ULS situations, but due to the importance of these, we have named it specially, and we did not name it ULS. Of course, they are in the ultimate limit state, but we have given them a special name. And for out-of-line components, I give you some imagination. What does that mean? The FLS is the verification during effects. You can do this with experiments, but you also can simulate this numerically. And then you have some requirements after impact, as you can see here. For in-plane load components, that's more or less the same, but they are with increased requirements because normally the in-plane components are part of the overall structure, and we have to care for that after the impact or after the breakage of a ply, the overall stability is not affected. And therefore, we have to care for that we have some dynamical effects, that we have residual capacity with a broken ply, that repair is possible, that the safe residual lifetime under repair is given, and so on. Now, this sounds possibly a little bit complicated, and that was the reason why we then have treated very much on this issue, and then we have decided that each country can decide which limit state scenario it is going to choose. So For a very simple thing, just a window, it is only SLS and ULS. Possibly the window is of no concern for the building authorities. In some countries, yes, in some countries, no. And up to the limit state scenario 3, where you have the full set of all 4 limit states, everything has to be considered. Now some design topics. I give you an overview here, of course. It's a little bit, there are many. Of course, we are very, very busy, so that's the result. In the first part, we are explaining and regulating the principles of limit states. We're explaining material strengths, partial factors, and the verification routes and stress design in ULS and SLS. Actions, for instance, we needed an improved rule on how to calculate the internal pressure of an insulating glazing unit, IGU, which is also very important for us. The structure analysis referring to interlayer modeling, so we are always now considering the shear coupling of different plies combined to a glass pane. Any other structural provisions they are given, and we have annexes on the bending strength, the resistance, who is an advanced model, and with a normal, traditional model. The thermal effects, cold bending is very important as well when you have a facade where you don't want to bring the glass in shape in an oven, but to bring it in shape by just forcing into a shape in the cold state. In part 2, there are then additional things, and there we have the verification rules for FLS and PFLS, and also we are then dealing with the connections and the supports. And in part 3, then we are doing this in the same way, but only considering that these things then are in plane or axially loaded, and that brings us then to very severe theory, second order or nonlinear effects, which we have to take into account as well. The key topics are glass types. We are dealing with anneals, all types of anneals, and all types of thermally or chemically treated, ranging from thermally toughened over heat strengthens also to chemically strengthened, and that is rather unique. Key topics are glass assembly, mono, laminate, IGUs, as I said. Design bending strengths, I dropped already some words on this. You can see here the intrinsic glass strengths will be added to a part of, which you can see there. It is the difference of the overall total design bending strength minus the intrinsic characteristic bending strength of the annealed glass, and that is the contribution of the pre-stress. And that we are then modifying with some factors accounting for the exposition, for the time, for the area, for the size, which detail we have, and so on. I think this is, it's a very high scientific level, but also easy to use. We also have now new rules, which are then dealing with the laminated glass. Laminated glass is characterized that if you have a short-term loading, it behaves monolithically. If you have a medium-term loaded, it behaves partially layered, partially monolithic, so what you're calling partial shear coupling. And if you have a long, very long, so everlasting loading, then it is like a layered. And all of these states you can consider with these kind of formula, which then have been developed for all kinds of plates, shapes, loadings, points, line loads, distributed load, and so on. And also depending on the temperature you have, for instance, coming from the sun. And that we have then included into a model, which we have then here in this code. And you can see that these are a very good approximation to finite elements, simulations, and so on. Here you can see the different schemes of load arrangements and boundary conditions. There are many more in the annex. It is only an excerpt. So, and let me finally give you some ideas on what we do in the part 3, where we have in-plane loaded elements. I give you here this image picture there. That is a recently erected double towers in Paris, Tour d'Or, where at that level we have here in the facade some glass fins, and the glass fins needed to be verified according to lateral torsional buckling, and we did the testing for this, and you can see how it behaves. So there is the laminated cross-section, and it twists and moves laterally. And for those elements, we then have now foreseen rules for buckling, like we do it in steel, but we are a little bit different because we try to incorporate all these loading scenario in one formula for one buckling. And these buckling curves then can vary from loading to loading. And you can see then this is the analytical approach, and this is the finite element analysis results. So it is a little bit easier in glass because it's perfectly elastic, and we don't have any so many different shapes. It's always rectangular, only that it is laminated or mono. These are the simplifications compared to other materials in this respect. I think I come now to the conclusion. Ladies and gentlemen, Eurocode 10, Design of Glass Structures, joins the Eurocode suite. It follows the principles of modern standards. It is taking into account the special properties of glass as building material. It is covering all topics of design in modern glass construction, and is offering maximum flexibility at the interface to national legislation. And Eurocode 10 is, like every Eurocode, fostering innovation. This would conclude my presentation, and I would like to say thank you very much for your attention. Thank you.
Thank you for this first glimpse into the upcoming Eurocode 10. Yes, please stay with me, and if the other colleagues could join us too. I'm sure we have a lot of technical questions. Let me get 2 organizational questions out of the way while the colleagues are getting ready. Everything you're listening to today, the presentations are already online in our download section, so you can download them, and the recording will be available on the DIBt YouTube channel in a couple of days. So, thank you for bearing with me. We have a new addition to this panel. Markus Knoblauch, the new chair of SC3, welcome. Mr. Knoblauch, you have recently taken over from Ulrike Kuhlmann at the helm of SC3. What are the key challenges awaiting you?
Well, I think actually Steve Danton actually reported on the overall scheme, and Ulrike Kuhlmann actually showed us the specific scheme and the specific challenges which were already with respect to the technical content of Eurocode 3, for instance. However, now we actually have to implement these rules into the engineering practice and actually already prepare the next steps for, let's say, after the implementation of the Eurocode rules in the engineering practice.
Thank you.
Okay.
Would you like to follow up?
Yeah.
I see you're burning to follow up.
Oh, sure. Let me say thanks to you, Carmen, and also to all of you, and also for the new Marcos. Now we have 2 of them. It's a little bit hard to communicate, but we will see. We continue to receive a multitude of questions and comments, especially in the Eurocode 3 part. So we will see how we bring that on the table. But let me say thank you first. It's interesting from you, Marcus, to see the new Eurocode 10. So my first question, and it's from my side, is it easier, you think, is it easier to create a new Eurocode or to change the other ones?
Oh yeah, I think the answer to this is a little bit manifold, because on the one hand, it is easier because you have freedom. You have your group, and you can shape the structure from scratch. You don't need to cope with something that has been given to you from the past. So that is what is good. The other thing is, it is at the same time the difficulty, because you are sitting there having a blank sheet of paper, and now you say, please write something. So, and then you have to organize yourself, and that means that for the first years were really hard to come together with different approaches, because in each of the countries, the look on design of glass is different, or has been different. Now we are a little bit merging together, and with the Eurocode, that is the first consensus document on design of glass. And now I think it gets easier as it was in the beginning.
I think the new Eurocode 10 will have a big impact to the glass structure market and also to new buildings. So I have a question for that, but first let me address a question for Ulrike. You mentioned some new methods, new models and so on, and I have the feeling that there is a lot of fear in the audience and in the chat behind that, that new models and technical background may be not sufficiently clear enough to bring it to an application. Can you take this fear?
I think it is a bit a matter of our task today. The title was that we should give the changes, the innovations. Very clear, the rules which are at the moment in Eurocode 3, they are valid, and they are transferred. It's really the same. Yeah, they are really transferred. It's an evolution on certain points, and maybe because the focus was on these certain points, the impression is. But in fact, the rules which we have in Eurocode 3 are valid.
Yeah. Okay. So that leads us to the next question. It's about the new part you mentioned for the numerical methods. So the question was, does finite element analysis, guidance, or covered nonlinear behavior, and especially nonlinear materials, are simplified and representative material curves provided?
I didn't get that. Can you repeat the last bit?
Are simplified and representative materials curves provided? So the question is...
Okay, yeah. There are. So we have a set of material curves given for different material, also for stainless steel, for example, and they are simplified, but they are also for more complex features given. So there are a number of material models given, as well as, I think, what is also very important, to give guidance on the imperfections.
Yeah. Okay, thank you. One question to Alberto. You mentioned in some of your slides that the calculation methods were simplified where possible.
Yes.
Could this potentially lead to an increase of consumption of material and are not aligned with our sustainability goal, or is it
most of modifications were related to the simplification of the mathematical rule, the formal aspects, in order to make it more friendly, more appealing to the user. But from the substantial point of view, the impact on the final weight of the structure is not so high. So in the end, the cost is largely unaffected by these modifications.
Okay, thank you. Thank you. My last point was for Markus Feldmann. there are 3 or 4 remarks or questions concerning the new fracture limit state.
Yes.
You call them FLS, and
FLS.
there was a discussion whether it was a good name or not because of the fatigue limit state. Maybe you can say something about that.
Yeah, when we have baptized this limit state, we never thought on fatigue limit state, and I recognize that could be the confusion. Possibly we can have a discussion on this, but in Glas it is already now a fixed term. Sorry for this, but fatigue to some extent plays a role, but not that major role in glass compared to steel or other materials. Yeah. Sometimes, but we have to talk again.
Okay. Thank you. Yeah.